All right, so as you have probably figured out, there was no video lesson 10 because lesson 10 is just a practice day in the classroom. But there is a lesson 11, and lessons 11 and 12 and 13 deal with some topics taking derivatives of some kinds of functions that don't really fit anywhere else, so they're here. On today's show, the derivatives of the inverse trig functions. The inverse trig functions will fit in our discussion right here. So that's the plan for the next 14 minutes or so. The inverse sine function, so that we're all clear, the inverse sine function, you may recall it from our pre-calculus work. The inverse sine function is the function where, let's see, we got to remember what this means. Y is the angle whose sine is x. That's what we mean when we say inverse sine. It's the angle whose sine is x. So what does that mean? Well, that means that the sine graph goes through pi over 2, 1, and so the inverse sine graph goes through 1 pi over 2. And the sine graph goes through negative pi over 2, negative 1, and so the inverse sine graph goes through negative 1, negative pi over 2. That graph is the reflection in y equals x of the sine graph with a restricted domain so that it passes the horizontal line test. So that function is smooth. And since it's smooth, it has a derivative. And if it has a derivative, we should be able to find it. And I think we will. What do we know? We know that if y is the inverse sine of x, then x is equal to the sine of y. And if x is equal to the sine of y, I can take the derivatives of both sides with respect to x. And the derivative of x is 1, and the derivative of sine y is cosine y dy dx, which means that dy dx is 1 over the cosine of y. Now here's the question. Can I get cosine y in terms of x? And the answer is yes. Consider a right triangle where this is the angle y. That's the angle whose sine is x. And the way to get its sine to be x is to have the opposite side be x and the hypotenuse be 1. There you can see that the sine of y is x. So this third side, by Pythagorean theorem, is radical 1 minus x squared, which means that dy dx for the inverse sine graph is 1 over the cosine of y. And that is something that we have to know. We have to know that the derivative of the inverse sine graph is 1 over radical 1 minus x squared. Similarly, let's take a look at the inverse cosine graph. The inverse cosine graph looks like so. It has endpoints at negative 1 pi and at 1, 0. This is a reflection in y equals x of the cosine graph with a restricted domain so that it passes the horizontal line test. That function is smooth, and since it's smooth, it's differentiable. I'm able to draw tangent lines everywhere. I want to draw tangent lines everywhere. I want derivatives. So if y is the angle whose cosine is x, then x is the cosine of y. And if x is the cosine of y, then the derivative of x is equal to the derivative of cosine y with respect to x. And we remember that y is a function of x. And if y is a function of x, you've got to put the derivative of y with respect to x right there at the end, which means that the derivative of y with respect to x is 1 over negative sine y. Well, can I get that? Sure I can. If y is the angle whose cosine is x, then that third side is, by Pythagorean theorem, radical 1 minus x squared. And the sine of y is radical 1 minus x squared. So the negative comes over, and so does the square root. You have to know that the derivative of the inverse cosine function is negative 1 over radical 1 minus x squared. Now, why does that almost make sense? Take a look at the red graph. Oh, I should copy stuff. Here we go. Okay, so let's copy stuff. If you take a look at the two graphs, the one is just a vertical flip and shift of the other. It's a vertical flip and a vertical shift. And if that is the case, then we expect that their derivatives are the negatives of each other. We expect that. So it actually is not a surprising result, not as surprising as you think it might be. Okay. I'll show one more. I'll show the inverse tan derivative. Inverse tan looks like so. We're well familiar that the asymptotes are at pi over 2 and negative pi over 2. On the actual tangent graph, the tangent graph has vertical asymptotes at negative pi over 2 and positive pi over 2. And that tells me that the horizontal asymptotes of the inverse tangent graph will be at negative pi over 2 and positive pi over 2. Those are big deals. So then what? That's a smooth curve. And since that's a smooth curve, we can take its derivative. If y is the angle whose tangent is x, then x is the tangent of y. And we can take the derivative of both sides with respect to x. Derivative of x is 1. Derivative of tangent y is secant squared y dy dx, which means that dy dx is the cosine of y squared. So what does that mean? Well, if I have a right triangle, and there's my angle y, and y is the angle whose tangent is x over 1, then the hippopotamus of that triangle is the square root of 1 plus x squared. And since that is square root of 1 plus x squared, that's just Pythagorean theorem, the cosine of y is 1 over radical 1 plus x squared, and I'm going to square that. You have to know that the derivative of the inverse tan graph is 1 over 1 plus x squared. You have to know that. You have to know it cold. So, why does that make sense? Well, let's think about this. At the origin is the steepest slope you're going to see. That slope is looks about 1 at the origin. And sure enough, this thing is as big as it's going to be when x is 0. Also, as we get larger and larger in both directions, those tangent lines are practically horizontal. As we get larger and larger in both directions, x values get bigger, denominator gets bigger, fraction gets closer and closer to 0. So this is actually very intuitive. In a similar way, in a similar way. I won't bore you with all the details, and they are boring. The derivative of the inverse cotan graph, which looks just like that but upside down and shifted, is negative 1 over 1 plus x squared. That's another thing you have to know. Now, granted, if you know the derivative of the inverse tan graph, and you know that the co-graphs are all flips and shifts, then you know, okay, I'm just dealing with a negative, but you still have to know that. In a similar method, by a similar method that I won't bore you with online. Oh, we'll go with colors. The derivative of the inverse secant graph is 1 over absolute value of x times radical x squared minus 1. And as if that wasn't bad enough, the derivative, oh, that's terrible. We're not going with that. We'll go with that. The derivative of the inverse cosecant graph is negative 1 over absolute value of x times radical x squared minus 1. Again, the relationship is the co-graphs, the graphs of the co-functions, have the opposite of the derivative of their actual functions. That's the basic idea in there. So those are 6 derivatives you have to know. Really, you have to know 3 and relationships, but you've got to be able to produce any of those. I feel bad saying that because it's going to come down to 1 question in a multiple choice section, maybe 2. But you've got to know it, or at least be able to derive it. So what's it going to look like? What's it going to look like? We're going to play everybody's favorite game, Find the Derivative. I'm just going to reinforce the chain rule for about 4 minutes, and then we're going to be done. I want to find the derivative. So how do I find a derivative? Well, I know that the derivative of the inverse sine function is 1 over radical 1 minus x squared. So the derivative of the inverse sine of 2x plus 1 puts a 2x plus 1 in that slot. And that's fine if I multiply by the derivative of the innermost function. This is chain rule at its most basic. The derivative of the inverse sine of something is 1 over radical 1 minus something squared. But then we multiply by the derivative of that inner function. And it's okay to leave the answer that way, because that's the way it's going to pop up in the choices. Similarly, let's see. Let's do x inverse cosine of x plus radical 1 minus x squared. Again, just making sure we've driven home some of our rules. That first part is the product rule. The product rule, it's so much fun. It's 1 prime 2 plus 2 prime 1. And then the radical, it's a square root function. The derivative of the square root of whatever is 1/2 times whatever to the negative 1/2 times negative 2x. And then let's clean some things up, because that's not the way it's going to show up as an answer choice. The first term is negative x over radical 1 minus x squared. Then we've got an inverse cosine. Then what have we got? We've got 1/2 canceling with 2. We've got an x in the numerator. And in the denominator, we've got radical 1 minus x squared. So this leads to negative 2x over radical 1 minus x squared plus inverse cosine of x. That's the way it's going to pop up as an answer choice. Is that okay? Wait a minute. Yep, that's it. That's what I'm hoping for. Okay, so there you go. There you go. Okay, yes? Yes, I got that right. Don't tell me I didn't. Very well. What do you have to know? You have to know that there are derivatives of these inverse trig functions. You have to know their derivatives cold, and you have to be able to use them with the other rules we've been doing. So if you've got those down, marvelous. That's what you want to be practicing. Tomorrow, exponential functions, because what could be more fun than exponential functions? All right, thanks everybody.